Okay, hello everybody. This is Mrs. Masteller. I'm here teaching you guys about section 8384, which is now graphing rational functions. And there's a lot of detail in this lesson, so I'll go kind of slow here, make sure everyone's good, feels comfortable with the matter. But there's a lot of stuff to know when it comes to graphing a rational function. This front page is more so just talking about the transformations of these, okay? And we're just talking about reciprocal functions. So this is kind of different from the rest of the lesson that we're going to continue on with the next page with. So it says at the top, a reciprocal function has an equation of the form f of x equals 1 over a of x, where a of x is going to be a linear function, and a of x obviously cannot be 0. The domain, which are your x values of a reciprocal function, it's limited to the values for which the function is defined. So there's limitations to this function, right? To determine the value of x for which the function is undefined, you want to find the value for the denominator of the expression that equals 0. That's how you know what makes it undefined. As again, you're basically asking yourself, for these first 4 examples, it says determine the value of x for which each function is undefined. What you're basically asking yourself is what makes this all 0 in my denominator, right? What's the one value that makes this undefined? Well, that would be 0 in this case. X cannot be 0. If x were 0, that would make my whole denominator 0, and that's bad. Makes it undefined. So for example number 2, what makes all of this 0 in my denominator? My one undefined value would be positive 3. For number 3, it'd be 3 over 2, 3 halves. For number 4, the last one, we got to factor it first. So that factors into x plus 8 and then x minus 3. So our two undefined values would be negative 8 and positive 3. Okay, so we've been practicing that for a while now, so hopefully that's easy enough, just knowing what makes it undefined. But those undefined values are part of the actual shift. Again, the whole vertical, horizontal shifts that we see. So this is the transformation equation, which we've been working with transformations all year long. Every single graphing unit that we've done transformations, right? We know what A does, we know what H does, we know what K does by now. H again is going to move the function either to the left or to the right. So it's going to be the horizontal shift, basically, the horizontal translation. But it's also going to be the vertical asymptote. So the vertical asymptote is going to be x equals h. So at x equals whatever our h value is. Vertical translation, so vertical, our k value, so h, again, moves it either to the left or to the right. And then our k value moves it vertically, which is either up or down, but it's also going to be the horizontal asymptote. It's going to be at y equals whatever our k value is. Okay, a now can either reflect it or compress it and expand it. So it's only going to be a reflection if a is a negative number. So it says the graph is reflected across the x-axis when a is less than 0. So if a is negative, if you have a negative a value, negative 1, negative 2, negative 3, negative anything, then it's going to be flipped over the x-axis. Okay, and the last one says compression and expansion. The graph is going to be compressed vertically when the absolute value of a is less than 1, but it's going to be expanded or stretched vertically. I usually say stretch, but it's going to be stretched vertically, expanded vertically if the absolute value of a is less or greater than 1. Okay? So, getting into the graphing portion, we want to graph each reciprocal function, identify the asymptotes, the domain, and the range of the functions. Okay, so for this first one, the vertical asymptote. Again, you kind of compare it up here. It says the vertical asymptote is going to be at x equals whatever our h value is. So x equals our h value. So looking at this function, looking at this guy right here, okay, compare that to the transformation equation. This is the transformation equation, a over x minus h and then plus k is over here. Okay, so it's at x equals h. So looking at our h value in comparison to what we have, well, we don't have an h value. So that means it'd be a 0. Okay, so we've got a vertical asymptote. So here's what a vertical asymptote looks like. It's basically just going to be a dotted line. Okay, it's not truly a part of our graph. I mean, it kind of is, but it's not the actual graph itself. The asymptote is basically a boundary line. Okay, an asymptote is something that you get close to, but you don't touch. Okay, you don't touch it, you don't cross over it. So like I said, it's a boundary line. As far as our domain goes, our domain is restricted to certain values. We can't plug in certain numbers for x. So for example, where is it restricted at? Well, the only restriction is that x cannot be 0. So technically my domain is all real numbers, it's just that x cannot be 0. I can plug in any number I want to for x in this problem, I just can't plug in 0. Okay? As far as our horizontal asymptote goes, what it says up here, our horizontal is going to be y equals our k value. So it's going to be y equals, now identify your k value. So k will be hanging out over here. Well, once again, we don't have a k value, so it's just y equals 0. So our horizontal asymptote, dotted line, again, just going through 0. And the limitation to our y's is that y cannot be 0. So basically, whatever your asymptotes are, that's your undefined value for your x and for your y. Okay? As far as graphing the rest of it, what you're basically doing, we could just kind of do this mentally, but I'll let you guys know, it pretty much ends up in the same spot every single time, unless you have a reflection or anything like that. But what you're going to do mentally is I just plug in random numbers for x. I can plug in anything that I want to. Again, I just can't plug in 0. So if I plug in, let's just say positive values, if I plug in like positive 1, for example, plug in positive 1 for x, well, I'd plug in positive 1, I'm going over 1 on the x-axis, and now what's the y going to be? Well, y is going to be 1 divided by 1. So that's just 1. So 1, 1 is 1 point on my graph. Well, if I plug in 2 for x, if I plug in 2 for x, what do I get for y? Well, I get 1/2. So I'm going to plot the point 2 and then a half. Well, what if I plug in 3 for x? If I plug in 3 for x, what do I get for y? I get 1/3. So I go over 3, I go up a third. If I plug in 4 for x, I get 1/4 for my y. So I go over 4, go up a fourth. So as you can see, these points get closer and closer and closer, okay, to the actual x-axis, but it's never going to actually cross or touch the x-axis. The bigger x's I plug in, if I plug in now 5 for x, what do I get? Well, I'd have 1/5 for my y. Okay, so again, these points get closer and closer to that asymptote. They don't cross it and they don't touch it. Okay, it just basically curves around and curves around and just kind of hugs around that asymptote. Okay, but that's positive numbers. Same thing happens in the opposite direction. What if I plug in negative numbers for x? If I plug in -1 for x, what do I get for y? I get -1. So -1, -1. Okay, plug in the next one. What if I plug in -2 for x? Well, if I plug in -2, I get -1/2. So there's my next point. If I plug in -3, I get -1/3. If I plug in -4, I get -1/4, and so on and so forth, right? So it's just going to hug around, curves around our asymptotes. Those are our boundary lines. Again, you don't cross them, you don't touch them. Okay? So for the next one, vertical asymptote again is going to be at x equals your h value, which would be +2. So the one restriction in our domain is that x cannot be 2. Okay, so our asymptote again, our boundary line is going to be at +2, right here. All right, our horizontal is going to be at y equals our k. Well, we don't have a k, it's just 0. So the one restriction is that y cannot be 0. So our horizontal from left to right, our dotted lines going through y at 0. And again, we could do the whole process, plugging in numbers for x and then solving for the y. Just can't plug in 2 for x. Again, that's where it's undefined. That's our asymptote. But what's basically going to happen? The whole graph just is shifted over. So from the origin, and everything's always referring back to the origin. In relation to our origin, the whole graph is shifted over to the left or to the right 2 units because our h is +2. So again, if you look at this function, since our h value is +2 in this case, the whole entire graph from the origin, from 0, 0, everything just shifted over to the right 2 units. That's basically it. So for the next one, our vertical asymptote again is going to be at x equals, and then our h value, which is 0 in this case. So what makes this undefined is that x cannot be 0. That's the one undefined value that we have. I can plug in any number I want to for x in this problem. I just cannot plug in 0. So we have a vertical at 0. So that's just basically the y-axis. Okay. Our horizontal is going to be at y equals our k, which we have one. It's 3. The limitation is that y cannot be 3. Y cannot be 3 because, well, we have an asymptote at 3. So here's our horizontal. And now from here, graphing this out again, you can just plug in numbers for x basically, and then solving for the y. So for example, if I plugged in like 1 for x, +1, I'd have 1 divided by 1, which is 1, plus 3, you get 4. So I'm plotting the point going over 1, going up 1, 2, 3, 4. Okay, but again, what happens is it's just going to hug around and curve around these 2 asymptotes. Okay, but again, the whole thing in this case, since you have a k value this time, k is +3, from the origin, everything just shifted up 3 units. Okay, so just using my transformations. This last one, we have an h and a k value. You got an h value here, you got a k value here. So our vertical asymptote is going to be at x equals our h, which is -3. But that makes it undefined, right? I can plug in any number that I want to for x as far as my domain goes. I can plug in anything I want to, I just can't plug in -3. Okay, because we have a vertical asymptote there. So 1, 2, 3. We do have this vertical asymptote going through -3. Oh, vertical. I did horizontal. Vertical. Going through -3. Okay. The next part, horizontal asymptote. The horizontal is going to be going through y equals our k. Our k value is -2. So that'd be y equals -2. And then again, our range for this one is limited. Y cannot be -2. So horizontal going through -2 would be right here. Okay, so now again, you could simply plug in numbers for x and then solving for y, but again, all ends up in the same spot. We got a piece here, we got a piece here. And there you go. All right. So now moving forward, getting into the actual rational expressions, rational functions. So it says an equation in the form f of x equals p of x over q of x. P of x and q of x are going to be polynomial expressions, but q of x cannot be 0. So obviously q of x in your denominator cannot be 0. The vertical asymptote. So as we already kind of saw in a preview, it's going to be a line that the function will approach. It approaches, but never crosses or touches. Okay. It's located where x is undefined for the q of x expression, since q of x is in the denominator. The horizontal asymptote, same definition. It's a line the function is going to approach. So it approaches this line, but sometimes, every once in a while, sometimes, there's kind of that exception to the rule every once in a while. It sometimes crosses or touches. Are we going to necessarily see that? Probably not. Okay, but here's the hard part, is knowing when do you have a horizontal asymptote. So you have to memorize this box right here. This is key. Okay, it's kind of more summarized over on the right-hand side, so I'll kind of walk you through this. But if you have a rational function, p of x over q of x, p and q again, they're both polynomial functions, in standard form with no common factors other than 1, the graph of f has at most one horizontal asymptote. So it says if degree of p, so if the polynomial on top, if the degree of the polynomial on top is greater than the degree of q, which is on the bottom, then there is no horizontal asymptote. Okay, so it says if top bigger than bottom. So let me give you an example. If you have your top function, let's say x squared, and the bottom one's just x. Okay, the top one obviously has a bigger degree, it's 2. Degree on the bottom is just 1. So in this case, you actually do not have a horizontal asymptote. I usually just write NA, so it does not apply to us, right? Or you could just say none. That's fine too. If the degree of P is less than the degree of Q, so now if it's kind of switched around, the horizontal asymptote is going to be through y equals 0. So if I switch this around, if I have a smaller one on top, x the first over x squared, then I do have one, it's just y equals 0. If the top is equal to the bottom, what you're going to want to do, if the degree of P equals the degree of Q, horizontal asymptote is going to be the line, y equals, you want the leading coefficient of each. Okay, so what does that mean? Let me give you an example. If I have, again, equal degrees, right? Let's say I have like 2x squared over x squared. So the degree is the same, right? Again, I want y equals, we want the leading coefficient of the top over the leading coefficient of the bottom. So what would that be in this case? It would be y equals, the leading coefficient on top is 2, on bottom it's 1. So it would be y equals 2. That would be my actual horizontal asymptote. Okay, so we'll see some more examples of this. You might have a hole in your graph too. So it's a point of discontinuity, or a hole in the graph is located where x is undefined for the q of x expression. What you want to do, what you want to ask yourself, finding the hole, you want to ask yourself this question. What cancels? Whatever cancels on the top and bottom from your p of x and q of x expressions is going to be the hole. Okay? So let's try down below. It says determine the equations of any vertical asymptotes and the values of x for any holes in the graph, so find the domain and range. Okay, so first step says factor the numerator and denominator, so let's do that. So it doesn't look like my denominator is factorable, so I'm just going to keep that 2x minus 5. Factoring the top though, this would factor into 2x minus 5, and then x plus 2. Third is factored. Okay, so step 1, done. Now it wants to know where is the function undefined. So what makes this undefined? Basically finding my domain, x cannot be 5/2. That makes it undefined. Okay, now it says where is a simplified function undefined? So if you simplify this now, well the 2x minus 5's cancel, right? So since I no longer have a denominator, there's nothing left in my denominator, well, I don't really have an undefined value anymore, right? There's nothing left. So as far as the simplified function goes, nothing makes this undefined. But since the 2x minus 5's cancel, what that means is there's actually going to be a hole in this graph at x equals 5/2. Okay, or 2.5. So 5/2 is the same thing as 2.5. So same idea. It says compare the degree of the top to the bottom. So we're talking about the original. Compare these degrees. So looking at the 2 degrees. Well, the degree on top is bigger, right? So my top degree, since it's 2, top degree is greater than bottom degree. So what does that mean? The top is bigger than the bottom. Let's go back up here. Top bigger says for the very first one, if top bigger than bottom, then you do not have a horizontal asymptote. So what this implies, comparing my 2 degrees, this is implying that there's no horizontal asymptote. That's usually how I abbreviate it, HA. All right, so let's try some examples on the next page. So not even just graphing yet, okay? We're just going to practice doing all these steps. First thing you want to do on the next page, first thing we're going to do is just factor. So factor everything out. So top, it's going to stay. Bottom, this factors into x plus 5, x minus 2. Okay, so what makes this undefined? -5, positive 2. The way I like to do it too is I like to find the horizontal asymptote first before anything cancels and anything goes away on us. So the horizontal asymptote, if you compare the 2 degrees, right? The degree on the bottom we can obviously see is x squared. We just have a 4 on top. Well, technically that's x is 0. We don't have a degree. The degree is 0 on top. So since my top degree is smaller than my bottom, right? 0 is less than 2. That would mean we do have a horizontal asymptote at y equals 0. Okay? Do we have a hole in this graph now is the next question. You're basically asking yourself, again, to find the hole, what you're asking, what cancels? Is anything going to cancel now that I have this factored? What cancels? I don't see anything that's going to cancel. So that means we don't have a hole in this graph. But we do actually have 2 vertical asymptotes. So because we have 2 values, 2 binomials still left in our denominator, these 2 will become our horizontal asymptote. We have 2 of them. And it's at the undefined values. At x equals -5 and at x equals 2, those are going to be your 2 vertical asymptotes. Okay, let's try the next one. Number 11. Factoring this out, you have x minus 4x plus 3. On top, on bottom, just take out an x. Take out a GCF. Okay. So there's 2 undefined values. It'd be 0 and then 4. And again, I like to do the horizontal asymptote before anything starts canceling and going away on us. So going back to the original problem, if you compare your 2 degrees, so on top you have x squared, on the bottom you have x squared, so we have equal degrees, right? They're the same. So now what you want are the leading coefficients, which would be just y equals 1/1, so y equals 1. Okay. Next thing, is there a hole in this graph? Again, you're really asking yourself, does anything cancel? Yes. At x equals positive 4, so at this undefined value, that's going to be the hole. The vertical asymptote is whatever's left in my denominator after I cancel. So what do I have left? I still have this, so that's going to be my vertical asymptote. At the other undefined value of 0, that's going to be my vertical asymptote. Okay, so what's left after canceling? I still have an x. All right, let's try the next one. Go ahead and factor away. So we got x plus 3 on bottom. Splitting this one up, you'd have 3x and x. Then we need -2. Let me see, this will be -2 here and then +1 over here. Okay, so for the next one, what makes this undefined? -3. Again, horizontal asymptote, if you compare, on top you have x squared, on bottom you have an x, or x the first power. Since the top is bigger, so it's kind of the opposite of the one right above it, the top one is bigger, so you actually don't even have a horizontal asymptote. Okay, is there going to be a hole in this graph? So does anything cancel? I don't see anything, so there's no hole either, but you do have a vertical asymptote. So what's left still in the bottom after trying to cancel? I still have that full binomial, which is going to be at this undefined value. That is going to be the vertical asymptote. So at x equals -3. All right, so the last one over here, factoring again, you got x plus 1 on top. On bottom, you got x plus 5x plus 1. Two undefined values, -5, -1. Now again, horizontal asymptote. Compare your 2 degrees. On top you have x the first, on bottom you have x squared. So since the top one is smaller, you do have one at y equals 0. Okay, is there a hole in this graph? Again, does anything cancel? Yes. So at x equals -1, there is a hole in this graph. Okay, the next one, vertical asymptote. Is there anything left in my denominator now after canceling? Yes. At x equals -5, I would have a vertical asymptote. All right, so there's all the steps for you right here. So find the vertical asymptote and holes if possible, draw them, use a t-chart to find points, and then plot the points and draw the graph. Here's the steps. So let's go through it one more time. Okay, doing the same exact steps, but we're also going to be graphing it now too. All right, so for the first one, first of all, what makes this undefined? +3. All right, again, let's find the horizontal asymptote before anything else. So compare your 2 degrees. You have x on top, x the first power. You got an x in the bottom. So since they're both x the first power, you want, again, the leading coefficients, which would be 2 over 1. So at y equals 2, you have a horizontal asymptote. So let's just go ahead and graph that. So here's my horizontal at y equals 2. Next, is there a hole in this graph? So basically, does anything cancel? I don't see anything, so there's no hole. But you do have a vertical asymptote. So since you still have all this left, you've got a vertical at that undefined value of x equals 3. Okay, so let's just go ahead and graph that now. X equals 3. Okay, so here's how the rest of this works, right? We need 2 pieces. There's going to be stuff to the left of my vertical and stuff to the right. So what I'm going to do is I'm going to set up 2 t-charts. We're going to plug in again numbers to the left of the vertical. We want to plug in numbers to the right of the vertical. So our vertical asymptote again is going through at +3. So you want to think of numbers to the left of 3. What's to the left of 3? Well, that would be like 2, 1, and then 0. And then think of numbers to the right of 3. So what's to the right of 3? Maybe plugging in like 4, 5, and 6. Okay, so we got our x's chosen. Now just actually plug them into the function and solve for the y. So when you plug in like 2 for x, you're plugging in everywhere you see an x, solving for your y. So you're going to have y equals 2 times 2 plus 1 over 2 minus 3. So that would give you 4 plus 1 on top, that's 5. And then I have 5 over -1. So 5 over -1, -5. Okay, plug in the next one now. So now I'm plugging in 1, and see what we get. Okay, so when I plug in 1 for x, we have 2 times 1 plus 1, so 2 plus 1, that would be 3 over -2. Well, 3 over -2 would be -1.5. Okay, I'll just kind of go through and fill in everything else for you guys. All right, so what else would we have when we plug in now 0 for x? If you plug in 0 for x, you should get -1/3 in the end, -1/3. All right, so now from here, just double check something. Okay, so now I want to plug in the other numbers for x. So I want to plug in 4 for x, 5 for x, 6 for x, fill in the other table. So if I plug in 4 for x, I'd have 2 times 4, which is 8, plus 1 is 9. 4 minus 3 is 1, so I have 9 over 1, so that would just be 9. Again, 5 for x, we would have 2 times 5 is 10, plus 1 is 11, 5 minus 3 is 2, so we get 11 over 2, and 11 over 2 is going to be about 5.5, 5.5. And then plugging in 6 for x, we get 12 plus 1, that'd be 13, and then 6 minus 3 is 3, so we get 13 over 3, and 13 over 3 would be about 4.3, 4.3 repeating. All right, so we got our points. Now let's just go ahead and graph it out here. Okay, so what are we going to have graphing this out? So what it's going to look like if I go over 2, and then we're going to go down 1, 2, 3, 4, 5, so it's all the way down here. And then over 1, going down 1.5, and then 0, negative 1/3, so on and so forth. So again, this one's just going to curve around, gets close to those asymptotes, doesn't cross it, doesn't touch it. There's the first piece. Okay, so that's all to the left of the vertical asymptote. Everything else now, the rest of these points, I wish this graph was a little different, but these points are going to be way off the graph. But going over 4, going up 1, 2, 3, 4, 5, 9 is somewhere obviously way up here, even past that. But then we have the point 1, 2, 3, 4, 5, 1, 2, 3, 4, 5.5. So again, this one's just going to curve around this way. Again, it gets closer and closer to those 2 asymptotes, doesn't cross it, doesn't touch it. Okay? So there's your overall graph. So let's try the next one, number 15. So let's factor everything. Factoring out the top, that'd be x minus 3, x plus 2. And the bottom doesn't factor, that's just x minus 3. So one number makes this undefined, that'd be positive 3. Okay, do I have a horizontal asymptote? So let's go back to the beginning here. Look at your 2 degrees, you have x squared over x to the first power. So if your top degree is bigger, you actually don't even have one. Okay, so there is no horizontal asymptote. There is no horizontal boundary line. Is there a hole in this graph? Yes. X minus 3's cancel. So at the undefined value of x equals 3, that's going to be my hole. Okay, from here now, is there a vertical asymptote? Is there anything left in my denominator? I don't see anything. So there's actually not a vertical either. Okay, so there are no boundary lines. It's not like the last one. There's no boundaries. So what am I graphing exactly? Well, what do I have left here? After I cancel, what I have left is just y equals x plus 2. That's what you're graphing. And you should recognize that that's just going to be a line in slope-intercept form. That's just y equals mx plus b. So you just have to remember, though, that there's going to be a hole at x equals 3. Okay, so I'll kind of put that in at the very end. I'm just going to start at positive 2 on the y. Slope is 1, so I'm just going up 1 over 1. You can also go backwards, too, if you like. But here's your graph. Okay, and there's going to be a hole at x equals 3. So what you're going to do, along your x-axis, count over to 1, 2, positive 3, go up to the line, and right here at this point, there's going to be a small opening. Okay, so that's not an actual point on our graph. So again, our domain is technically all real numbers. It's just that x cannot be 3. That makes it undefined. Okay? So there you go. Now you've seen a hole. On to the next page. So the next one. Let's factor everything first. So factoring out the top, that'd be x minus 4, x minus 2. Underneath, this would be x minus 2, x plus 1. So what makes this undefined? 2 and negative 1. Okay, do we have a horizontal asymptote? So going back to the original problem, compare your degrees, x squared, x squared. Well, now we want the leading coefficient, so at y equals 1. Okay, so at y equals 1, here's our horizontal. Okay, now walk yourself through. Is there a hole in this graph? Yes, there is. These cancel. So at x equals 2, so again, at this undefined value, there's going to be a hole. Is there a vertical asymptote? Yes, there is. This is still left, right? So that's going to be my vertical, which is the other undefined value at x equals negative 1. So if x equals negative 1, now you're going to draw a vertical. And now, since we do have these boundary lines, right, it's not just going to be a line anymore. What we need, set up 2 tables. Again, you want to plug in numbers to the left of the vertical. And then you want to plug in numbers that are to the right of the vertical. So left and right of the vertical asymptote. So the vertical is going through negative 1. So if you think of numbers to the left of negative 1, I'd probably plug in like negative 2, negative 3, negative 4. And then plug in numbers to the right of negative 1. I would probably plug in like 0, 1, and 2. Okay, so now from here, you want to plug these numbers in for x and solve for y. Here's the kicker though. Here's the better part. You don't need to plug these numbers into the original problem. You can if you want to, but if you look, you'll be plugging it into this x, this one, and this one. Okay, it's going to take a little while. What makes it easier, plug it into what you have left. Okay, what's my remaining function? After I canceled, all I have left is x minus 4 over x plus 1. Plug it into this one. It's a lot easier to calculate. Okay, so if you plug in these numbers for x, on top you would have negative 2 minus 4 is negative 6, negative 2 plus 1 is negative 1, so negative 6 over negative 1 is positive 6. Okay, next one, you get negative 7 over negative 2, so that'd be 7 over 2, which is 3.5. Plug in the next one, so negative 4 would give you negative 8 over negative 3, so we get 8 over 3, which would be just 2.6 repeating, or about 2.7, if you will. All right, plug in the next one. So plugging in 0 for x, you get negative 4 over 1, so that's just negative 4. Plug in 1, you get negative 3 over 2, so negative 3 halves, which would be negative 1.5. Plug in 2, you get negative 2 over 3, so negative 2/3. As a decimal, that's just negative 0.6 repeating. All right, so graph these points out. So we got negative 2, 6, so going back to, going up, 3, 5, 6. Then we got negative 3, and then going up 1, 2, 3.5. And then we have negative 4, going up 1, 2.6 is about right here. All right, so here's this piece. The other one, now graphing this, 0, negative 4 would be down here. And then going over 1, going down 1.5, and then going over 2, going down about 0.6. All right, the one thing we can't forget though, okay, we're done graphing. The one thing we can't forget is the hole. There's a hole at x equals 2. So technically, we actually have that point in our table. Right here, there's actually going to be an opening. It's going to be undefined at that point. So at 2, that last one that we just graphed, that last point right here, it's actually going to be open at that point. So if you want the full ordered pair, the hole, right, if you know it's at the x of positive 2, well, if you just plug 2 in for x, you get negative 0.6 repeating for the y. That's finding the actual point for the hole. So if you want the actual ordered pair, that's what you're going to do. Just plug in that number for x and then solve for the y. Okay? The next one, let's go through this one now. So factoring, we have x minus 2x plus 2 on top. And obviously can't factor this. What makes this undefined? Positive 2. Do we have a horizontal asymptote? Compare your 2 degrees. You have x squared over x the first. So since the top one's bigger, you do not have a horizontal asymptote. Is there a hole? Yes, there is. At x equals 2. So at the undefined value, is there a vertical? I would say no, because, well, there's nothing left in my denominator. Okay, there's no more undefined values in this problem, so there's no vertical. So once again, kind of run into what we did a couple problems ago. All we have left that we're graphing is this, y equals x plus 2. So that's just, again, a line in slope-intercept, and there's a hole at x equals 2. So here's how this works. You can even kind of put the hole in as we go. So we're starting at positive 2, right, on the y. Slope is going up 1 over 1. Here's the hole at x equals 2. So you can even see where x is 2. My next point, again, that's going to be the opening right there at x equals 2. Otherwise, just put the hole in at the very end like we did in the previous problem. Okay? I got a couple more left here. So here's the next one. Let's see, this one's going to be a little bit more complicated now that I'm looking at it. That's okay. It might be good for you guys to see this problem. So factoring, you have x minus 1. The bottom, x minus 2x plus 2. All right, 2 undefined values, 2 and negative 2. Do we have a horizontal? So if we compare the degrees, x the first over x squared, yes you do. It'd be at y equals 0. Is there a hole? No, there's not. Nothing cancels, right? But you have 2, yes, you heard it right, you have 2 vertical asymptotes at x equals 2 and x equals negative 2. What does this look like? Well, the horizontal again is at 0. So that's just the x-axis. And then we have 2 verticals at negative 2 and also at positive 2. Okay, so here's our boundaries, right? Can't cross them, can't touch them. What does this mean? How do I plug in numbers? Again, we've always been referring back to the vertical asymptote. Well, you're going to have three regions altogether, right? You're going to have x's plotted to the left of the vertical, x's in between the two vertical, and x's to the right of the far right vertical, the one that positive 2. So you'd have to set up 3 tables in all, 3 xy tables. So again, as far as choosing numbers, you need to choose numbers that are to the left of x equals -2, between the vertical asymptotes, choose x's in between those two, and then choose x's that are to the right of x equals +2. Okay, so plugging in numbers. If I want to plug in numbers to the left of -2, I'd probably plug in like -3. We'll just do a couple, -3, -4. In between, I mean, there's not very many numbers to choose from, so in between -2 and +2 is only -1, 0, and 1. I mean, there's more numbers than that, but what makes sense to plug in is probably choosing whole numbers. The next one, choose numbers now to the right of +2. I'm going to plug in numbers like 3, 4, and 5. All right, this is going to be fun. So now, plugging in these numbers, you could plug it into the factored form if you want to, or just go back to the original. Since nothing canceled, there's really no easy way to do this. Okay, so if you plug in, I'll just kind of fill in the chart for you guys, and we'll see what this looks like in the end. If you plug in -3, you should get -0.8. If you plug in -4, you should get -0.42. All right, and then they just kind of keep increasing there. If you plug in the in-between part, -1, you get 0.6 repeating. If you plug in 0, I got 0.25, so 1/4. If you plug in 1, you get 0. Okay, and the very last one now, if you plug in +3, I got 0.4. If you plug in 4, I got 0.25. And if you plug in 5, I got 0.19. So those just get smaller and smaller. Okay, so what is this going to look like? Let's graph it out now. So -3, -0.8. So going back 1, 2, 3, down 0.8. So that's almost to 1, right? Almost to -1. Then going back 4, going down almost to -0.5. So here's this piece. It's just going to kind of curve around just like that. Okay? The middle piece is interesting. So if I graph this one, -1 going up 0.6, so just a smidge above a half. And then we have 0, 0.25, so let's just add a fourth. And then 1, 0. Here's what the middle one looks like. All right, if we plugged in more numbers, if we plugged in like, 1.5 or -1.5, we would kind of see it having this kind of behavior. So you can see it actually crosses over the horizontal asymptote, which we said sometimes it does do that. Okay, are you necessarily going to see it in problems? Not really. Okay, every once in a while though, you will have a problem just like this where it actually crosses over the horizontal asymptote. Okay, and the last piece, graphing these points. So we got 3, and then going over, we're going up 0.4, so it's almost to a half. Close enough. My calibration here is a little bit off, that's okay. Going over 4, going up 0.25, so it's just going to get closer and closer to that asymptote. Okay, it gets closer and closer to 0. Just kind of curves around in these two directions. All right, so pretty much the same idea too for the last one. As you see, nothing's going to cancel, right? So you would end up once again with 2 vertical asymptotes. So this one again, if you guys want to try that out, pretty interesting overall, but I think you probably have seen enough for today. If you have questions, per usual, just come to us. We'll be more than happy to help you. But there's your lesson on graphing rational functions. Thank you.